So look over here. We completed till over here, isn't it? Solid sphere, hollow sphere, and all these cases, isn't it? Now, for these cases only, like I want to discuss the particular, like if I see for hollow sphere, we calculated my electric field or not, and that same electric field concept is applied on the particular solid conducting sphere also, isn't it? And non-conducting hollow sphere. Now, when we have calculated our electric field, we should also know the particular value of potential for the hollow sphere, isn't it? So look over here, let's start. We will calculate today the cases like potential of hollow sphere and potential of solid sphere. Potential of hollow sphere. Got it or not? So let's suppose if I take a hollow sphere. Okay, this is my hollow sphere and oops, for this hollow sphere I want to find my potential. Now I told you that this has some charge q, okay, on the surface, because on the surface it will only lie, and this hollow sphere has some radius r. Okay, then we got two important conclusion over here, that the electric field at an external point, at any external point located at a small distance r, is given as 1 by 4 pi epsilon naught. It means it behaves like, it feels like that the whole, our whole sphere for the external point behaves like a point charge, isn't it? And that charge is kept at center. Is that clear or not? Okay. So if it is a point charge and it is kept at center, so the radius means the distance of this point is how much? R. So electric field can be given as what? 1 by 4 pi epsilon naught q by small r. Q by small r's. So you should always treat, means Hardami, if you have any kind of external point and if there is a symmetrical configuration, which kind of configuration? Symmetrical one. Then you keep that particular charge as a point charge on the center. Is that clear or not? Yeah. And similarly, we calculated our electric field at the surface point for this hollow sphere, and that electric field was simple. Let us write it fast. E was 1 by 4 pi epsilon naught q by capital R square, and electric field at any inside point is how much? Zero, isn't it? That's how. That's what our conclusion was. Okay. So look over here. Basically, we will utilize this term only to find the potential. See, for an external point, if I want to find the potential, it's very simple to find potential at external point. First point. Look over here, which is located at point P. Means I'm trying to find the potential at point P. Are you able to get me or not? Now, to find the potential, see how to calculate the potential. Potential is not an easy calculation. The reason for that is, I told you that in case of potential, we have, you look over here, we need to select a reference point to do the calculation of potential, isn't it? So look over here, like we did so many questions regarding that. Wait. See, when we are doing this kind of calculation, we need to define our R initial for it. For any kind of case, work energy or potential energy or potential, whatever we wanted to define, for that we need to define our case of initial point. Are you able to get me or not? Hi, so without defining initial point, we will not be able to get the potential. Are you able to get me? So look over here. Basically, how to utilize this concept over here, we will see that. So let's suppose if I want to find, first case is external point or outside point. ठीक है? That means R is greater than capital R. Is that clear or not? Now look over here. Potential formula is what? Potential is given as, I told you that day, it is given as integral E dot dr vector. Isn't it? So potential over here will be what? Minus electric field at point P, we know that it is kq by r square. R square and dot dr, isn't it? But look over here. See, if I want to utilize this potential concept, I told you that day that potential is 0 at infinity, isn't it? Potential is 0 where? At infinity. So basically, according to logic only, the whole question answer means you should write it as not. This is the important thing which I should write. That potential is 0 only at infinity, normally. ठीक है? So that means our reference point should be actually what? Infinity, isn't it? Because from there only I can start my calculation because there only my potential is 0. Are you able to get me or not? So therefore, we consider this integral. Yeah, so we consider the calculation measurement from infinity to radius r where my charge is, where my field is considered. Yes. So 1 by r square का integration minus 1 by r होता है. तो I'll write directly. You can write as 1. Okay. So this I can write r 1 by r square as r to the power of minus 2 dr, isn't it? This is r to the power of minus 2 plus 1 divided by minus 2 plus 1. So it is minus 1 by r. ठीक. So look over it, minus minus will become positive, kq will be outside and it will be 1 by r from infinity to r, isn't it? And 1 by infinity is how much? 0. So potential at point P is given as formula. Look over here. Potential at point P is given as just simple K capital Q by R or 1 by 4 pi epsilon naught Q by small r. Is that clear? Are you able to get me? Yes. And at so at surface, the potential will be simply at surface the potential will be K Q capital R. But what about, see, inside my electric field is 0 or not? So does my potential will also should be 0? Ideally, yeah, you said yes, but actually you should know. अरे बाबा तुम खुद सोचो, याद करो, electric field was change in potential by change in distance, dv by dr, isn't it? So if electric field is 0, change in potential is 0, not my potential. So that means we need to prove something. So look over here at inside point. How come you can directly say means r less than capital R? Is that clear? So look over here at inside point. If I want to find potential at, let's suppose I call this as point I. ठीक है? Potential at point I, which is inside point. Now try to see. My electric field was varying 1 by r square till the surfaces, and inside it is 0 or not. So I have two kinds of electric field, isn't it? So once again my calculation integral I should apply infinity to inside point which is small r at I E dot dr, but there are two electric fields, isn't it? So for the integration should be taken for two electric points. So first I should come infinity to surface and then simply E dot dr which is for outside and then minus E dot dr from r to center. Are you able to get me or not? Got it? So this value is already equal to 0 or not? Why? Because electric field inside the region is how much? Inside the particular surface is 0. Are you able to get me? Inside, look over here. Here my electric field is 0 or not? And this integration is taken from R to center only. So यहाँ से electric field 0, तो यहाँ पे potential भी 0. Means ये term 0. Is that clear or not? So look over here, if I do this integration, once again, you will see that I'm getting once again E, keep the value of E over there. So it will be minus K capital Q by small r square infinity to capital R dr. So once again I'll get minus 1 by r over here. So it will be kq outside 1 by r and infinity to capital R. So that means kq by capital R. That's my potential at inside point also, which is equal to 1 by 4 pi epsilon naught capital Q by capital R. Are you able to get me or not? That's what I told you, that electric field is zero. That means change in potential is zero. Outside potential is kq by capital R. So inside potential should be also same, because it is, if electric field is zero, it is creating which kind of a surface? Equipotential surface. Are you able to get me? Is that clear? So if I want to draw graph of this, are you solving HC Burma perfectly? Really? You have to solve it. Are you solving the DPPs? Till how many DPPs you have completed? There are total 23 worksheets in that. Tomorrow I want, tomorrow 20. Okay, I'll tell your mom to check the homework tomorrow. ठीक है? Okay. So now look over here. If I want to plot, there are two reasons. One is inside R less than capital R and R greater than capital R. So look over here. Inside it is equipotential surface, so the potential will remain constant. And outside the potential is decreasing slowly and it's trying to become zero. So outside potential diagram will be like this. Is that clear or not? ठीक है? And this point is R is equal to capital R. This point is K capital Q by R, and this potential for outside varies as 1 by R. Is that clear? So remember, for hollow sphere, the potential inside is not zero. Similarly, for conducting sphere also, potential inside it is not zero. It will be an equipotential surface. Whatever the potential of surface will be there, same will be the potential till the center. Is that clear? Chalo. So let us utilize. Means we calculated electric field and potential for the hollow sphere and conducting sphere. Similarly, we will do the calculation of potential for non-conducting sphere. Day before yesterday, we calculated the electric field, where we got to know that inside electric field varies linearly, while outside electric field varies inversely proportional to R square, isn't it? So let us apply the same concept. Potential for non-conducting sphere. Now once again, you know that potential at infinity is zero. So we will always consider the integration with respect to infinity. Non-conducting solid sphere, let me write. ठीक है? चलो. Now look over here. If I consider the solid sphere, once again I have three different points. One external point, one surface point. Are you here? And one interior point. Okay, let me name it as ABC. because we use charge Q. Take. Now try to see. Once again, for exterior point, the electric field was given as 1 by 4 pi epsilon naught. I'll write it in a simple form here. E at kq by small r square. Simple form. At surface, E at B kq by capital R square. Inside, it was totally different. E is kq small r by capital R cube. Are you able to get me or not? So these are my three different electric fields. Now let us consider that this solid sphere is charged with capital Q charge. Are you able to get me or not? Okay. So let us write. Let's suppose the solid sphere have charge capital Q. Okay now. Is that clear? Now let us apply this concept. So I want to find the electric field at an outside point. First case. For outside point. Now for outside point, as we know that for any symmetrical case, it will behave like a point charge, isn't it? And electric field will also be same. So their potential can be calculated using this same formula, and I'll get 1 by 4 pi epsilon naught. How much is my charge inside that sphere in divided by r, isn't it? So for outside point, yeah, for outside point, electric field is same. It follows the same rule, 1 by 4 pi epsilon naught q by small r square. So our potential will be also same, 1 by 4 pi epsilon naught q by r. Is that clear? Similarly, for surface point, electric field at surface is given 1 by 4 pi epsilon naught q by capital R square. So potential over there also will be same. Yes. Are you able to get me? So the question arises, what happens for the inside point, for inside point or interior point, which is r less than capital R. Now here my electric field suddenly changes, isn't it? It's not zero, it suddenly changes. So I'll have to do the integration. Once again, I'll have to follow that potential at internal point case. So infinity to, I'm coming at r inside, so a small r, E dot dr. Now this will have two reasons, minus infinity to 1 to surface, because they varies as 1 by r square, while inside it is varying as linearly. So I'll have to do the integration, two different integrations, isn't it? R to a small r, because I'm calculating at a small r, no? A dot dr. Are you able to get me? So look over here, V at C is equal to minus infinity to capital R. This varies as kq by small r square dr minus, this varies something different, that is r to capital R kq small r by capital R cube dr. Are you able to get me? Now for first term, simply we know that integration 1 by r square dr is minus 1 by r, isn't it? So I'll implement it over here. If I implement it over here, it is kq will be outside 1 by r infinity to capital R. But here kq by r cube is common and r dr will have. So r dr is r square, isn't it? So r square capital R to small r. Is that clear? So this is our potential term. Now look over here. V at C can be found out easily. It is uh, k cube by capital R minus Oh, sorry, I forgot to put r square by 2 will be here. Okay, so it will become capital Q by 2 r cube into bracket. It will be r square minus capital R square. Is that clear or not? So V at C will be KQ by capital R minus KQ small r square by 2r capital Q minus it will be KQ by twice R, isn't it? If I multiply the whole term, so I got something over here. It will be something LCM. This is KQ by half of this. So I'll ultimately get KQ by 2R, isn't it? Are you able to get me? ठीक. So look over here. This BC will be KQ by 2R minus KQ R square by 2R capital Q. Are you able to get me or not? I think something. Acha, 1 minute. Sorry. Yeah, I did a silly mistake. Here minus and minus will become plus or not. So 3KQ by 2R minus KQ R square by 2R cube. Are you able to get me or not? So I can take VC is equal to what to be common? I can take KQ by 2R common. I will take this as common. And then I can multiply capital R square over here. So it is 3R square minus a small r square. This is my potential at internal point. Are you able to get me? Yeah, so it's totally different. So B at C is given as, means this is given as, I'll write 1 by 4 pi epsilon naught Q by 2R cube and then the whole term 3 capital R square minus small r square. Is that clear? So that's why we write in a very simple form. So V outside is simply KQ by R, V surface KQ by capital R, but V inside is totally different, which is KQ by 2RQ 3R square minus small r square. And this implies potential at center is not zero. So potential at center, which means the small r will become zero. So this is 3KQ by 2R. Are you able to get me or not? So let's suppose if someone told you to draw the graph of potential with respect to position, then it's not a big tedious task right now. We know that potential is never ever zero, isn't it? And its maximum value, because at infinity it is zero, isn't it? So its maximum value can be only 3KQ by 2R, which is at the center. Are you able to get me? After that, the potential will constantly decrease. So the graph will not be like increasing or decreasing, it will constantly decrease and it will ultimately become zero at infinity. Are you able to get me or not? Is that clear? And this is that point. Somewhere over here, potential tries to minimize. Take where, see, if you look over here, in previous cases, or you can see that there is a particular, in terms of electric field, there is a particular sharp turn over here or not. Suddenly from linear it goes as inversely proportional, isn't it? So that's why here also we have a sharp decline at one point where the electric field changes its proportionality and where the slope of potential becomes suddenly negative. Look over here. In integrate, if it is R, then the slope is positive. Here the slope is totally negative. Are you able to get me? So slope first increases and then it starts to decrease suddenly in the negative direction, and that is at KQ by capital R. Yes. Is that clear? Are you able to get me? Okay, so this is so many things we got from our hollow sphere and solid sphere. We calculated the potential and electric field all for all the cases. You just need to keep in mind if it is a solid sphere and it is non-conducting, then the density starts to vary and the charge in start density is constant and charge starts to vary. Are you able to get me? In some questions, it's specifically in HC Verma from question number 40 to 45, you will see that they have given the questions of density which is varying. So you need to definitely calculate the charges inside these smaller spheres and then you need to do all the calculation. Okay, ठीक है मेरी बातें समझ में आ रही हैं? Okay, now give the heading. Let us have a now we will not calculate the potential of many cases. We will discuss only the electric field of some cases, some exceptional cases. Okay, potential is your task to calculate. Okay, so give the heading field due to infinitely long or in the it's a very big and write it directly infinitely long charged hollow cylinder of charge density lambda and radius capital R. Are you able to get me? So we have infinitely long cylinders of some charge density lambda and radius r, and we want to find the electric field and all these cases. Are you able to get me or not? So let us see how to do all these things. ठीक है? So look over here, it has some radius r and it is going till infinity. So once again, acha, it is a hollow cylinder, no? I took the wrong cylinder. 1 minute. I have to consider a hollow cylinder. ठीक है? Cylinder समझ में आ रहा है ना ये? This looks like a cylinder. Yes. Okay. So let's suppose if it has a radius r and it has a linear charge density lambda. Are you able to get me? Now I want to find, let's suppose the charges are positive charges on it. I want to find the electric field due to this solid cylinder, hollow cylinder over all the point, exterior point on the surface and inside point, isn't it? So one thing I am damn sure, inside point electric field will be zero because if I consider a Gaussian surface inside, yeah, it's a hollow body. Are you able to get me? So let us do the first case. At outside point means R greater than capital R. Now look over here. It's your task to think. If I consider at an external point P where R is greater than capital R. Now you tell me what kind of surface should I make? What kind of Gaussian surface I'll get? No, I just want what kind of Gaussian surface I'll get. Yes, you should consider the Gaussian surface, no? How you are going to close this cylinder? Without Gaussian surface, can we apply Gauss law? No, no. In a simple logical way, the Gaussian surface which you are going to get is also going to be a cylinder. But this cylinder will be of some finite length, because for infinite I can't find easily. So we need to enclose this whole body in a Gaussian surface of a finite length. Are you able to get me? Is that clear or not now? So you got the idea how to enclose a cylinder? Consider a Gaussian surface of length L itself. And this Gaussian surface is itself a cylinder. तो लिख लो cylindrical Gaussian surface. आई बात समझ में? थोड़ा अच्छे से लिख लेते हैं. Now think of electrical field. How many kinds of area we have for cylinder? So you can say only circular surfaces and curved surfaces, isn't it? Yes. So I will have, see, look over here. If I consider a small region, see, if I just consider a small region for this small area, the electric field will be in the same direction, and the area will be also in same direction, area vector. Is that clear? And if I consider a small circular means a small area on this circular surface, then what? Why come flux is how come? Where is electrical? How come electrical field vector is perpendicular? Means you are saying that there are no charges on the circular surface. How come there are? That's what I told you. So do not learn physics. Yes, there are no charges on the circular surface because it's an infinite surface. So we will not consider it's a hollow cylinder. So then this is not a disk, but this is a ring. So how come the charge will be on this circular surface? It's a hollow cylinder now. Okay. So the electric field are only due to the curved surface. That's why the electrical fields are perpendicular to my area vector of curved circular surfaces. Is that clear? बात समझ में आई? ठीक, अगर ये सर्कुलर सरफेस है, इसमें एरिया वेक्टर क्रॉस का मतलब बाहर आ रहा है ना, और इलेक्ट्रिकल फील्ड कैसा होगा? ऐसा, क्योंकि सरकमफ्रेंस पे चार्जेस हैं, तो क्या होगा? हरदम एरिया विल बी परपेंडिकुलर टू द इलेक्ट्रिक फील्ड, इजंट इट? So therefore we'll write the flux equation for it, that we know that flux will be equal to, since we are trying to find through Gauss law, so we will calculate through flux, isn't it? So flux will be integral E vector dot dA. That means I'll have two components of flux, integral E dot dA for curved surface and one plus integral E dot dA for circular surface. And this must be equal to charge enclosed by epsilon naught. Are you able to get me? Now for circular surface, as these are perpendicular, so this value is exactly 0. Are you able to get me? So this implies phi is equal to E integral dA, which is equal to Q enclosed by epsilon naught. This implies E dA. What is the total integration of surface area of all this Gaussian surface? That will be 2 pi r into L, isn't it? Are you able to get me? Because see, I want to find, let us consider, means if I want to find the electric field, I'm considering my electric field over here only, means at this point. Is that clear? This is my point. Okay. And the electric field and dA are pointing away from there. Wait, let me draw it perfectly. This is my small r, such that I will not have to draw another Gaussian surface. So this is the direction of electric field, and this is in the same direction I have my dA vector and dA. Okay? Are you able to get me? So integral dA will give me what? E into 2 pi r L is equal to Q enclosed by epsilon naught. Are you able to get me? So that means I got E is equal to, and Q enclosed is charge Q means but charge is not given. I have been given lambda, isn't it? So charge enclosed, that means charge enclosed will be how much? Lambda is charge by length, isn't it? So in this Gaussian surface, the charge enclosed lambda into length L. Are you able to get me? So I'll just put it equal to lambda into length L by epsilon naught. So LL got cancelled, and ultimately I got my value of electric field at an exterior point, that is lambda by 2 pi epsilon naught r. Is that clear or not? Is that clear? So if I multiply by 2, and so it will become just simple 2k lambda by r, which is similar with the case of infinitely long wire. Is that clear? Are you able to get me? So you have to always take care of this. You have to always this. Mm-hmm. ठीक है ना? So and outside point interior, E interior case 2, E interior is 0, simple, and E surface will be same 2k lambda by capital R. Are you able to get me? ठीक है? Now, if I look over here, then as we know that electric field is a vector quantity. So if I write for electric field as a vector quantity, that is 2k lambda by small r into r vector. That's how I'll sorry, r cap. Now r cap is 2k lambda r vector by r square, isn't it? So now look over here. The question arises that what is this r vector? Can you tell me? That's the direction of what? Mm-hmm. Of the electric field. Remember, r vector, right? R vector is the position vector of point with respect to the axis of the cylinder. So you need to keep in your mind that if I consider r vector, then it should be with respect to the axis of cylinder. Are you able to get me or not? Just like, let's take an example. If the axis of cylinder lies on y axis. So look over here. If the axis of cylinder is lying on y axis, that means what? The circle, ध्यान से समझना जरा, मतलब सिलेंडर की खुद की एक्सिस y एक्सिस पे, तो जो सर्कल बनेगा वो xz प्लेन पे बनेगा ना. तो जो r वेक्टर हम बनाएंगे वो x वेक्टर और z वेक्टर के हिसाब से बनाएंगे. इज दैट क्लियर और नॉट? So you have to always keep in mind for the electric field vector of the cylinder that r vector is taken with respect to axis of cylinder. If axis is in x axis, then r vector will be in terms of y and z axis. Are you able to get me? So look over here. Therefore, we write over here r vector as, if the cylinder axis is on y axis, r vector is xi cap plus yz cap, and in that form my electric field vector will be given as. Is that clear? Okay. Now, sometimes the if the cylinder is given, they do not give lambda of the cylinder. Sometimes they give sigma of the cylinder because it behaves like also surface density, isn't it? So, right over here, relation between lambda and sigma of cylinder. Is that clear? So let's suppose we know that charge on the cylinder means if I follow lambda, then lambda is q by L. And sigma is q by total surface area, which is 2 pi RL, isn't it? So simply if the charges, basically whatever happens, the charges on the cylinder will same. So that means lambda into length L must be equal to sigma into 2 pi RL, isn't it? Or this gives us the relation between lambda and sigma. So lambda is equal to sigma into 2 pi R, which you should always remember that if lambda is given or if sigma is given, you have to be cautious and use that form of this form of the equation for the given cases. Are you able to get me? So two cautious points are there. One is in the case of consideration of r vector, and second in the consideration of charge density. Which thing is given, you have to always keep in your mind. So electric field inside the cylinder is 0. Once again, you can draw the diagram of E versus R, and it will be similar just like previous case, but it will be varying 1 by R. Are you able to get me or not? Sure. So let us move on to next point. Let us give the let us do the case of electric field for uniformly charged infinitely long solid cylinder, non-conducting. Okay, conducting, similarly we here also this value, this thing is applicable for conducting solid sphere. Are you able to get me? Because once again, for conducting case, the charges will be on surface only. So long solid cylinder which is non-conducting. Are you able to get me or not? Now once again, try to find. Let us see. Try to do the calculation by yourself. Specifically for the inside point. You do the inside point. Outside point is known to everyone. Do it by yourself. Try take 2 minutes specifically for inside point. Okay, and the cylinder has मैं लिख दे रहा हूँ linear charge density lambda और linear charge density is given. Okay, and radius capital R. And also you can we'll see the relation between volume charge density and linear charge density. Hmm. Outside point it is going to be same, isn't it? So let yeah. But what about the circular surface? What about the circular surface? Tell me. Uh, thing. What about the circular surface? How come? Charge is spread all over here or not? Yes, then for them, was my electric field was zero for the disk? Was the electric field at the surface of disk was zero? Really? Or it was sigma by 2 epsilon naught? Yes, it was not zero, isn't it? Does my electric field will be zero over here for circular surface? Hmm. Think. Acha, let's suppose if I construct a Gaussian surface. The answer lies for you, like these kind of questions can be asked and they are confusing. So draw a Gaussian surface. Tell them that I will draw a Gaussian surface and then I'll tell the answer. Now when you draw the Gaussian surface, you got your answer. Why? Because when you draw the Gaussian surface, it will behave like it is only a disk of charges and my point lies over here, isn't it? So I need to consider the electric field. I told you that for them the electric field will be in same direction. Why I am not considering the upward electric field? Because that are balanced by the positive charges over here. And due to repulsion, all these electric field from the upward direction will be cancelled out. Is that clear or not? So that is why the electric field and the area vector for the circular region is also making 90 degrees just like the previous case. Is that clear? So look over here. This is length L. मेरी बातें समझ में आ रही है ना? So now I'm considering this as my outside point, which is located at a small r. The radius of the circular disk is r. And for here, the electric field is in the same direction, and dA also it is in same direction. For this reason, dA and the electric field is in this direction, while the dA is perpendicular to it, isn't it? Are you able to get me? So once again, for outside reason, the solid cylinder behaves like hollow cylinder. ठीक है? And that is why E outside is simple. It is lambda by 2 pi epsilon naught r. Are you able to get me or not? Which is written as 2k lambda by r, which is also E of infinite wire. Is that clear? मेरी बातें समझ में आई? Now the question arises, what happens for the inside point? Isn't it? As in that. Once again, if I want to find for the inside point, I need, if I will consider an inside point over here, then I need to draw the Gaussian surface inside over here, isn't it? So look over here, I'll draw it. I'll draw it, wait. And once again, I'll get a cylindrical Gaussian surface. But here, the charge content will be different or not. So same thing, same equation. Flux is equal to integral E dot dA. Two reasons are there, circular surface and curved surface, isn't it? So, so integral only for, it will exist for curved surface, because for circular surface it is 0. Are you able to get me or not? So this implies flux is equal to integral E dot dA. E dot dA is E. Integral dA, because once again it is a cylinder. So I'll take a curved surface area, isn't it? That must be equal to charge enclosed by epsilon. But question arises that how much is my charge enclosed? Are you able to get me? Yes. So now look over here. It's a 3D solid object or not. Although my lambda is given, I need to consider what? Volume charge density, isn't it? We don't need to consider. Means we will consider in terms of rho, then we'll express in terms of lambda. Is that clear? So the point is, one thing we got to know. See, the point is, outside we are considering lambda, but inside I need to consider rho. That's the biggest mistake over here. Are you able to get me? Okay, so that means we need to establish a relation between lambda and rho. Are you able to get me or not? So in question, remember that if they are asking outside, they will definitely give lambda. for NEET, and if they are asking inside, they will definitely give rho, and on some questions they will definitely give both lambda and rho. Are you able to get me? So look over here, charge enclosed will be how much? So see, the total charge, if I am using rho, then we know that rho is equal to total charge by total volume. So that was Q by, what is the total volume? We do not know because it is an infinite charge, isn't it? So if I want to write for this Gaussian surface, then rho should be equal to charge enclosed divided by the volume of this Gaussian surface or not. So which is how much? 2 pi r square L, isn't it? Sorry, not 2 pi. How much? Pi r L. Is it pi r L volume? Pi r square L. Are you able to get me or not? Pi r square h is the volume of cylinder or not? So charge enclosed is how much? Rho into pi r square L by epsilon naught. So L got, okay, integral dA in terms of Gauss surface. So look over there, you can see one thing, that whatever thing I am applying, if I am applying the flux rule of Gauss law, I will must apply on the Gaussian surface, not on the whole body. Is that clear or not? So when you apply integral E dot dA, this means this dA means that it's an area of the Gaussian surface, not for the whole body. Are you able to get me? I am saying that when I am applying Gauss law, I must consider only the Gaussian surface. I must not consider the whole surface. So look over here, integral df. This means that this area must be, means you can write it as like note. I'll write it at the end that when you apply Gauss law, it must be for the Gaussian surface. So E into 2 pi RL, sorry, 2 pi RL is equal to rho pi r square L divided by epsilon naught pi r cancel, LL cancel, and E inside varies as for inside region, since it is an infinite body, so it is rho L by 2 epsilon naught. It's rho L by 2 epsilon naught. Are you able to get me or not? Sorry, not rho L, rho R. You are not concentrated, Srishti. Previously, your mind used to be here. Whatever I am saying, you are saying it's correct. So that's my electric field inside the solid cylinder. Is that clear? And this is why we can establish the relation between lambda and rho. So lambda into 2 pi RL is equal to rho into pi r square L, isn't it? So this must be the relation which should be followed between lambda and rho, so as to, if any kind of incomplete information is given to you. Is that clear? So look over here. See, I can write in terms of charge, but this is an infinitely long cylinder. That's why I need to write in terms of rho. Remember that even here for solid sphere, I can write E in terms of rho over here. See, I calculated E inside it, which is QR by 4 pi epsilon naught R cube R naught. So here, instead of applying, instead of charge given, I can have also the rho value. So look over here. If I write in terms of rho, the Q enclosed is given as, okay. So right over there also in terms of rho. That's a very important conclusion which we draw. In terms of rho, Q enclosed is how much? Q enclosed, see, I'll not know capital Q. So Q enclosed is rho into 4 by 3 pi capital R cube or not. Small r cube, isn't it? And electric field is what? Electric field inside, it is 1 by 4 pi epsilon naught q by small r square. कुछ तो बोलो हाँ ना. तो अब q की हम वैल्यू q enclosed basically in that region. So E over there is k into 4 रो नहीं के को रखो I'll write wait 1 by 4 pi epsilon naught rho into 4 by 3 pi r cube divided by r square. So look over here, r cube r square cancelled and pi got cancelled, 4 got cancelled. So this electric field inside the solid sphere in terms of rho varies as rho r by 3 epsilon naught. Are you able to get me or not? So for inside region, remember that non-conducting solid sphere, we have E as either QR by 4 pi epsilon naught r cube, or it is also equal to rho r by 3 epsilon naught. While for solid non-conducting cylinder, it is rho r by 2 epsilon naught. Is that clear or not? So this is the main conclusion over here which I wanted to draw. Are you able to get me? ठीक है? Chalo. So this was all about your derivation of different cases of potential and all for cylinder and sphere cases. Are you able to get me or not? Now let us do some problems related to Gauss law. बोल रहा है कि let's suppose there is an annular spherical surface okay. This is radius r1 and this is radius r2. The total charge in this region over the surface means I'll write the question. बोल रहा है a hollow sphere ठीक है. It is not considered here. Let me write a hollow sphere of inner radius r1 and outer radius r2 okay, have charge q. Then find E at A, B and C. I'm marking the points. A is outside, this is point A, okay, or no, this is point C, and then we have point B over here, and then we have point A. Again, A is located from center at A distance, B is located from center at B distance, and C is located from center at C distance. Is that clear? बताओ. Mm-hmm. It's written hollow sphere. बताओ क्या होगा इसका आंसर. I think our 8 classes of electrostats are over. In 2 more classes, your electrostats will be over. Then 3 more classes we will require for capacitance. Okay, dipole is left. Then we'll start conducting conductors and capacitors at the same time. Okay, conductor and capacitor. That will take 3 to 4 days. Okay, बताओ क्या होगा. Should I do? I do one take 1 minute. Can I do? Try. 1 minute.